There is all comments coming here.
Okay, no problem. I can speak, that's all right? Directly I can speak.
Yes.
Okay. So people will come now or what?
Yes, you can start, sir. People are coming.
Oh, I have to see camera here, is it?
Yes, sir.
It's a problem here actually. I see there, I see here the problem.
There is camera, sir.
Yeah, but see, you should keep them here, no? Why you are keeping here? See, you should synchronize, isn't it?
Yes,
you
sir.
keep like that, I can't see this. If I see this here, this guy goes this way, right?
You can read here also, sir. This is only your comments, sir.
Okay, can you focus this?
Oh,
Oh, here's a problem, okay. So what is this?
You are live, sir.
Huh?
You are live.
No, I'm not putting my hands there. Why is it going like this? See?
That is previous, sir. This is like live. You are live now, sir.
Okay.
There is YouTube. They are coming live in YouTube.
Arey yaar, I talk now it's coming here now, right? It takes so long or what?
No, actually कुछ सेकंड है ना वो बफरिंग हो रहा है तो प्रॉब्लम चलती ये हो रहा है सर.
You forget it, man. What you guys are talking, I don't understand. If I'm seeing this after 5 minutes, how do I talk here?
Sir, you are right now you are live. There is streaming, sir.
Is it now being streamed now going on outside?
Sir?
Is it now being streamed outside?
No, sir.
Are you telecasting right now?
Yes, sir.
No, stop, na.
Sir, session is going on, sir.
Okay. So what do you do? I mean, somebody will ask questions now, or what is the situation?
Yes, coming with question, yes, sir. Someone.
Yeah. Good evening to all of you. Welcome to this live session. And I hope you people had good interaction, good learning experience with the videos of the NPTEL. So today we are supposed to have some discussions on the questions that we have actually. So before we start, what I want to say is that the course is mainly structured in two aspects. The first aspect is the basics. The basics is one, the thermodynamics of the corrosion. The second is the kinetics of corrosion. So these two aspects is very important that we understand them somewhat, in details. If you have a good clarity on this thermodynamics and kinetics, then solving the industrial problem becomes very easy. In the course also, we start with the basics of the electrochemistry and the kinetics of corrosion. And when we go along understanding the various forms of electrochemical corrosion or various types of corrosion mechanisms, we again invoke the thermodynamics and kinetics so that you know how do you apply them for various forms of corrosion. So we will talk about the various forms of corrosion at a later stage. Today we shall focus on understanding the kinetics. What do I come to understand that we have about 11 lectures going to be completed this week, and with that I think the thermodynamics and kinetics becomes almost over. Discussion is going to be over. So I want you to has any questions that any of you have in all these videos that you have been observing actually. Now I received some kind of questions here. I will start with answering these questions. Then any more live questions that you have in mind, suppose you have come across some kind of doubts in the intervening period, we can discuss that as well. So let me just go here. How do I change this to the board? From here, how do I change to the board?
Control N.
Control?
Tab.
Okay.
Alt
Alt tab?
Alt tab.
Oh, then it goes here. Okay.
And then you go slides here. Tab and
Then?
Alt tab.
Again same?
Yes, sir.
Oh, 2 times you have to do it. Okay. Alt tab.
Alt tab. So first Alt, then tab. First Alt.
Oh, first Alt and then tab. Okay. We again gone back to this.
So third one is the slide, sir.
You see Alt, okay.
Tab.
Tab.
Tab. One more.
Huh?
One more time, sir.
Tab. Tab.
Yes.
Okay. There is one question regarding what is the meaning of reaction coordinates. I think we are talking this in relation to the transfer coefficient. Okay. If I recall it, what we have seen is that you have energy versus the coordinates diagram. This is the energy, this is the coordinates or distance. You see how we are struggling to write on this board as compared to a blackboard. So if you consider that the reaction, let's say, between A is turning into B, the A is a reactance and B is a product. You know that this reaction is possible only when there is the free energy change is going to be negative. It's going there now?
Yes, sir.
Do you have to repeat again?
No, sir. Please.
Earlier whatever written here is gone or not gone?
No, sir. It's going, sir.
No, earlier I finished talking, na?
Yes, sir.
That is already, people are hearing that or not hearing?
You can start again, sir. Cut it from, sir.
Okay. So let me start this again because there's some glitch in the recording system. The question is, what is the meaning of reaction coordinate in the graph at this particular time? One more suggestion for all of you is, if you can make a little bit more specific. For example, I have also seen a similar question like that, have a question about what is happening in this video at 00.30.29. Just another question, another link. Now I think, of course, the first question is a little bit more clear. The second question is not very clear. So I would suggest that we just make the point a little bit more precise. Okay. Okay, so let me go back to this question. That is, what is the meaning of reaction coordinate in the graph at the time? I think what is shown at the time is regarding the activation energy concept. Okay, and it's very similar to chemistry. Okay, suppose we have a reaction that is, let's say, A is into B, and we said that the free energy change for that is negative. I think we said that thermodynamically the reaction can occur. But then the reaction does not occur normally because the free energy change for the reaction is negative, but there is a activation energy barrier for that. So we are discussing this in that, the slide there, in terms of what causes the activation energy barrier. If I represent in the diagram the energy states of A and B, this is the energy here, this is the coordinate, okay, and the energy of A here, the energy of B. Now it goes through activation energy state and comes down like this. Now the transition from A to B occurs because the energy difference between B and A is negative here, right? The A has got higher energy, B has got lower energy, and when transforming from A to B, the energy is liberated, that is given in terms of the free energy change. But why is then the reaction from A to B is very difficult? Because the A to transform into B, it has to go through an intermediate stage of let's say A and B a complex. It goes through a route, this is called as a route here. It goes through a route, and at that route this complex has a higher energy as compared to the B, understandable. Okay. So when I say reaction coordinate from the state A to state B, how it is getting transformed? It is transformed through a route. Okay, and that is what is represented here as a coordinate, okay, or as a distance. Either way that you can take it. In simple terms, this point means that is the energy required to form this activation complex. An intermediate stage between A and B, which has got this high energy actually. Okay, so the coordinate here means, graphically speaking, a state where A and B is a transition state, right? And from that transition state it goes to B. Okay, so that's what here it represents, if you want to call it as a distance, because sometimes in the diffusion processes it has to go through certain distance, and the coordination changes and so on. So that's what is represented here in terms of what we call as the coordinates, the distance. There is another question that is related to what would be the effect of hydrogen pressure on electrode potential if certain metal activity not equal to 1 is immersed in sulfuric acid solution. This question, of course, you have to see in the light of corrosion here. Now, let's visualize this. So, what you are saying is that you have a sulfuric acid, right? And if I am going to dip a platinum electrode, for example, right? And this is sulfuric acid, right? And this is a platinum electrode that you see here, right? And then you are going to shield this with hydrogen. You know, suppose I bubble this with hydrogen gas into this. Now there is hydrogen gas is present in the system, and the sulfuric acid gives you H plus ions, right? Now in this case, please notice platinum is noble in this case. The platinum does not take part in the reaction. So what is the equilibrium in this case? The equilibrium in this case is between H plus electron gives you hydrogen. That's all I think, right? Now the electrode potential we talked about, right? E is governed by the Nernst equation, which is E naught plus 0.059 by N, and the activity of H plus upon the partial pressure of hydrogen that we talk about. When this is in integral form, so we're going to put a square root of this actually, and N is 1 in this case. So if you are changing the partial pressure, assuming the concentration of sulfuric acid is going to be the same, now the potential is going to change, right? So all you need to do is that you need to write a Nernst equation, right? When you write a Nernst equation, and you will be able to know how the hydrogen influences the potential of the metal. So this is a simple hydrogen equilibrium that is taking place, right? On the other hand, if I am going to talk about a metal which is active metal actually, right? Let's say I am placing a pure steel iron here, iron metal, and it's a sulfuric acid again, right? And we are going to now pass hydrogen gas to this, okay? Okay, so you might be maintaining certain partial pressure of hydrogen, whatever pressure is possible. You can maintain, right? But the difference here is that when iron is immersed in sulfuric acid, it suffers corrosion, right? Let's say iron sulfate and you have hydrogen is getting liberated. You can convert this into electrochemical reaction, as I've been saying before. You will notice that there are going to be two types of equilibria that is going to be existing. The one equilibria you can write as H plus electron gives you hydrogen, right? And there is going to be another equilibria with Fe2 plus 2 electron gives you iron, right? There are two equilibria that we have. Please notice the equilibrium potential of this would depend upon the concentration or activity of H plus and the partial pressure of hydrogen that we talk about. So E would depend upon the concentration of hydrogen or activity of hydrogen more precisely, and the partial pressure of hydrogen that is present in the environment. It only depends on that. It's not going to depend upon the concentration of Fe2 plus at all. So the Nernst equation is very much applied here, right? So that is going to be the equilibrium potential of the system. So that is the equilibrium potential is irrespective of what the metal is. However, when you are going to have a metal like iron which is corroding now, so what is going to happen is this is not going to maintain an equilibrium, right? The similar way, iron also has an equilibrium potential. It is again given by the concentration of, or more precisely, activity of Fe2 plus ions. So you have an equilibrium potential for this, right? This is Fe2 plus and Fe. Here the equilibrium potential is for H plus. Here. The only difference here is that when these reactions occur on the same metal surface, the equilibrium potential will not remain, they start shifting. That is why we call them as mixed potential theory. Mixed potential theory, and then that also leads to the corrosion potential, we all know about it, and also the ICAR that we all know about it. Okay, so in this case, the hydrogen partial pressure is only one aspect of it that determines the ion potential here. It is now decided by both the equilibria of Fe2 plus to Fe, the equilibria of H plus and H. Okay, so that is to be seen in the light of that. So when we talk about sulfuric acid solution, and we talked about the equilibrium potential or electrode potentials, it will be seen in the light of that. If it is an equilibrium potential, it simply depends upon the concentration of H plus and the partial pressure of hydrogen as far as hydrogen is concerned. Similarly, the equilibrium potential for iron 2 plus and iron will depend upon the concentration of Fe2 plus. But it is seldom you can retain the equilibrium potential because these two potentials are going to be different, and so there is going to be polarization. So ultimately you will end up in ECAR and ICAR values. I hope the point is clear to you. So I will also come to the question that is displayed here later. Okay, let me finish off these questions which I received earlier. Okay, so there is also a question related to how do we apply mixed potential theory for prediction of corrosion? Yeah, so what do we mean by prediction of corrosion? One is to predict the corrosion potential, other is to predict the corrosion current density, right? Now the mixed potential is now is theory is applied based on the Tafel relationship, right? We talk about a Tafel relationship. Or if you want more precisely, you can use a Butler-Warmer equation, but that is a little more complex. All the mixed potential theory that we discussed in the class so far is using the so-called the Tafel equations. In the Tafel equation, what you have done primarily is we considered as the activation control. And you recall again what is activation control? It is the over voltage required to pass certain current so that the reaction occurs on the metal surface. And here it is not at all diffusion control. The migration is not the main aspect of it, right? It is only the charge transfer at the metal surface. Either iron is getting oxidized as Fe2 plus, or H plus is getting reduced as hydrogen, is what is happening at the surface here. So the simple Tafel lines, Tafel equations is what is governing the corrosion rate. Now there are some complexities. What are the complexities involved here? Sometimes it can be diffusion control. Sometimes you may not know the equilibrium potential when you talk about alloys. See, when I'm going to look at alloys, for example, we don't have any equilibrium potentials. So you can't write Reynolds equation. But in the laboratory, you can get a Tafel lines for an alloy. But then, why are we really interested in the mixed potential theory? If you see all my lectures of the kinetics, you will be able to understand what are the governing factors that control the corrosion of the metals. Or let me put it other way around. Suppose I measure a corrosion potential in an industry. In industry, suppose I want to monitor corrosion. One of the ways to monitor corrosion is to measure the corrosion potential. It's very easy. When the corrosion potentials are measured, you need to get an idea about the corrosion rate, right? How will you get that idea? That idea will come from understanding broadly the mixed potential theory of the metals. So that is where it is important. For a pure metal, yes, the mixed potential theory can be very easily applied, and so it's no problem at all. But complex alloys, we can still able to do it, provided you know the Tafel equations. But however, again, the equilibrium potentials for pure metals are not really known actually. Okay. Now there is another question wherein it reads as follows: we have a gas flow line what is made of Inconel 625 tubes. This line has many welds joints also. These tubes are exposed to 850 degrees Celsius. Hydrogen moist is flowing through these tubes at 850 degrees Celsius, and outer skin tubes is seeing air. My question is any chance of hydrogen damage of IN 625 tubes at a given conditions? Of course, this is more of a problem solving things, and such kind of solving problem you will be able to do it only when you complete the course, because this is, analysis of the problem involves a deeper understanding of the corrosion. Just to give an answer, I can tell you that the hydrogen per se will not lead to any problem at that particular temperatures. Okay. Some of the problems you will see later. The hydrogen leads to hydrogen damage, which means decarbonization, hydrogen induced cracking, hydrogen blistering, or some of these problems you will see towards the end of the course. I'm going to talk about it. And it is very unlikely that you'll have a problem. Of course, it's a moist. That means there may be water present, and the water might get oxidized. Probably can oxidize the inconel alloy, and I believe that because there is hydrogen, you're not going to have any kind of oxygen present in the system. Okay, so there may be some steam oxidation at that particular temperature, because the temperature is quite large actually. But hydrogen damage is very unlikely to happen at that condition. The next question is, what is the effect of concentration on corrosion? Yeah. Now, if you look at the concentration, there are two aspects to concentration. When you change the concentration, if you look at the taper lines, right? How do I change here? Yeah. I go to next slide, is it? Okay. So, see, this kind of problems will arise, in industry, or typically the problems are always complex. So, how do I really analyze the problem, right? And you've seen that if you look at the difference between a chemical reaction and electrochemical reaction, you all know, right? The rate of the reaction for a chemical reaction is a function of what? A function of concentration, the temperatures, right? And then of course the pressure that we talk about. These are main that changes the rate of reaction. If I take the electrochemical reaction, the rate of reaction is a function of what? It's a function of, again, concentration, temperature, pressure. One more thing, what? That is your E potential here. Okay. So it has a very same function. It can very much similar to what you see in the chemical reaction. Okay. Now, for example, the concentration can change the equilibrium potential, right? E is what? Suppose you have any electrochemical reaction, an oxidizer combines with electrons, giving rise to a reducing species, and the equilibrium potential E is equal to what? You guys know that it is equal to E naught plus RT by NF. I simplify this as 0.09 N, and the activity of oxidants upon the active reactants here. Now, what does the concentration do? The concentration changes the driving force. Potential is a driving force for that. Okay, so it can do this. What else it can do? You can also change the exchange current density. Okay, the exchange current density is a function of what? Is function of the concentrations. If the exchange current density changes, for example, without even going to Butler equation, I just go, let's say Tafel equation. Let's go to Tafel. Eta is equal to, let's say, plus or minus beta logarithm of I upon I naught, right? If I naught changes, eta changes, and this also will change. So any of these problems, don't try to get the direct answer. Try to get the relationships. How are the governing relationships in the electrochemistry, right? Then you can able to find a solution to specific issues. Okay. So I would like you to think in that manner actually. Okay. So that you will able to answer not only this question, you may able to answer several questions on that. Yeah. The next question that we have is how to find E. How to find E. How to find E. That is equilibrium potentials when the concentration is, let's say, some x, right? Forget about 0.01 whatever. Some is concentration, right? What is the governing equation? This is the governing equation, right? So if you are very clear about the governing equation, you don't have to remember things. Don't remember things. Don't get into ad hoc analysis. Go into the basics of that, right? So that is what I think is important in learning process. Okay. Yeah, so there are some questions now, you guys. For example, somebody says, what do we mean by cavitation corrosion? I think you have to wait for it, huh? So I will not be talking about the cavitation corrosion now. We have a detailed lecture on cavitation damage. We have a detailed lecture on various forms of corrosion. So I think let us defer that time, and again same Sanjit, right? How can we determine the maximum temperature attained by the bubble during cavitation corrosion? I don't think this question is much to do with corrosion. It is more of chemical engineering and maybe some of mechanical engineering, that I think, right? You should use that, the governing equation, for you to solve the problem. Okay, it is not related to corrosion at all actually. And I think Shashagiri Rao, I think at equilibrium delta G equal to 0, rate of deposition of electrode is equal to rate of ionization of metals. What will be the energy source for migration of ions from electrode to solution and vice versa actually? Okay. Yeah. This of course is a good question, right? And so what is the what is the energy of things? Okay, see that is basically because you have two energy levels, right? You have two energy levels. Can I go back to this actually? So let's look at this now. Let's look at this as a visualization of that. Okay. Suppose, let's say some metal, maybe hydrogen is, or maybe let's take iron for example, goes as Fe2 plus, and this guy is going back to this here. Okay. So you have the iron that is, so it's a kind of reversible things. Now yeah, see at these conditions, what we are talking about, the which is we call as equilibrium conditions. Okay. The potential that is so here, right? For example, assume that this guy, okay, the potential that is so established on in this metal surface, okay, let's say we call them as 0.44 volt is the voltage that we talk about, right? That is the voltage that is developed between the metal surface and the iron because of the exchange between the Fe2 plus and Fe at all, right? If there is no exchange of these two between these, for example, between let's say iron and Fe2 plus, even the so-called potential will not arise on the metal surface. And so the potential that is so developed here is happening only because these metals are getting exchanged between the metal surface and the metallic ions, or maybe gaseous ions, or the gas as well. So the movement of this is happening because the energy of this species that you see here, okay, on the, in fact, if you happen to see some of the STM thing, that is scanning tunnel microscope, you see these atoms in fact jump from the metal surface to solution and then they go back to the metal surface. So you can able to see it. In fact, I have seen the videos taken for the scanning tunnel microscope, because these are called local perturbations. So what happens is that initially, suppose the metal is quite, I would say the energy state of metal is, let's say, some X or Y, something like that. On transfer of iron to the solution, the energy of this metal is now changed from X, let's say, to Y. Okay. But the system is trying to go back to the system here and here, okay, because now there is an imbalance between these. So what happens in all these cases, you cannot say that the energy of this state and this state is going to be same. They are different, of course. We have seen it in the coordinates actually. But what happens is the energy separation between the state A and state B, overall energy separation is not too large. It goes back to this. So when we talk about reversibility, the energy between the state 1 and state 2, that in terms of actual changes, these energies are going to be very infinitesimally very small. So the guy can go back and forth. In fact, if the energy is going to be too large, you're going to make it, it's not going to go back at all actually. So in all the equilibrium systems, the energy differences, you also see like a Carnot cycle, for example, between the state 1 and state 2, if they are energy wise they are differing too much, it disturbs the equilibrium system at all. So what is happening is that is a small imbalance that happens actually, and because of this imbalance it goes back to the state. Okay, so that's how this equilibrium is maintained in almost all cases, all electrochemical systems. In fact, electrochemical systems are good examples of equilibrium. If you want to conduct an equilibrium reaction, chemical reaction in the pure chemical reaction, is not possible at all actually. Only electrochemical systems you can have a good demonstration of the equilibrium systems, because there's slightly changes, the energy difference between these two are going to be not too large. I'm talking about overall system energy. I'm not talking about the energy of the atom A, energy of the atom B, but we are talking about energy of the system A and system B. They are marginally different and it goes back to the state. That's how the equilibrium is really maintained actually. And this is, I'm not know what is it. Okay, Raghav, is it? Okay, Raghav, okay. For voltaic cell we apply voltage, what is that, minus V, is it? Minus V to the cell, whether we have to add voltage to the equilibrium potential or subtract from the potentials. Can you elaborate on that? I am not able to understand the question. Raghav? For voltaic cell, if we apply a voltage, okay, to the cell, whether we have to add voltage or to the equilibrium potential or subtract the potentials. Can you elaborate on that? Okay, so can we go back to this slide here? Yeah. Let me go to this question here, okay? I will not answer a question in that way you are asking. I am going to ask, I am going to, oops. What happened? Looks like so, okay. See, this is called as a shortcut method of, finding answers, okay. You are talking about, we apply voltage, for voltaic cell, you apply voltage. Now when you apply voltage for what? Now any cell has got 2 electrodes, right? There are going to be 2 electrodes. The cell has got 2 electrodes. Let's say, oops, what's happening? Okay, fine. Thank you. Yeah. So let's look at this question a little more broadly, right? Let's take a cell. Okay. The cell has got 2 electrodes. One may be positive, other may be negative, whatever kind of things. Now, from our convention, positive is the one where there is anodic reaction, right? The anodic reactions occurs at the positive electrode, right? Anode is positive for our convention, and the cathode is negative in our convention. Okay. Now, what we should apply here? Let's assume that, let's look at this, which is anode. What I should apply here? Assume that there is a reaction at the anode, there is an equilibrium, some equilibrium taking place. Let's say some X plus electron, some X is the reaction, right? Now, what is the anodic reaction? The anodic reaction is an oxidation reaction, right? That means X has to go as X plus electron, like this. Now, assume that the equilibrium potential for that is some E is equilibrium potentials, E value. Now, in order that this reaction has to become the anodic reaction, in order to do this, you need to polarize this into anodic way. That you have seen in the case of over voltage, right? What is the over voltage? E applied minus E equilibrium of that is equal to over eta. Now, what is eta here? If eta is going to be positive, you see, then anodic reaction occurs. Okay. Now, if this occurs here, if the eta is going to be positive, it occurs here. Now, how is it possible when eta is, eta can become positive? If the E applied is going to be greater than E equilibrium, then what happens? Then eta becomes positive. That's how you do that. Now, the cathode, what happens now? There is some reaction, some equilibrium that you have. Let's say Y plus electron gives you Y is in equilibrium. Now you have some equilibrium potential, some potential potential. Let's say E1 is the equilibrium potential. How does this reaction becomes a cathode? Then in this case, this occurs. Sorry, it occurs like this. For this, what happens? Eta has to be negative. That means E as E applied has to be smaller than equilibrium. So what you do? At this place, you increase the voltage, your value becomes more, it's happening. Here the value becomes more, here the value becomes less. Okay, so okay, so then the reaction starts occurring at the cathode, at the anode here. Okay, so this is what is happening in any given cell. So that means when the cell is open, you have higher cell voltage. When the cell is closed, you'll see that the voltage drops but the current comes out, right? So that's what happens in any cell actually, okay? So I hope you understood the concept here. Please use this concept of overload. This is the concept. Huh? Don't go into discussion like should I apply negative voltage, positive voltage, and it's very difficult for you to find an answer because there are be so many combinations that you normally see. Okay. Yeah. The same Raghav has asked one more question. Oxygen reduction potentials, which equation govern in acidic, neutral and alkali conditions? Actually, you can use the same. You can use, I mean, for example, you can use 4H plus water, right? It's about 2 water, right? 2 water giving us 2H2O, right? Okay. You can use this. You can apply the same. You can apply to whether it is neutral or alkaline, acidic, same thing applied. I don't think you can have, okay? But if you want to, you can go for, you know, neutral and alkaline, this one. That is, what is the other one? You have 2H2O plus 4 electrons and oh man, I think I made a mistake here, okay? Sorry, huh? Yeah, see, actually I'm sorry for that. I think you can use this equation, that is 4H plus plus oxygen there plus 4 electron gives you water. This is equilibrium potential for that. I think it is E naught for that is plus 1.22 or 1.23 volts, like this, I think, okay? You can use same thing, you know. It should be valid irrespective of what you know, equilibrium that you're going to use. Same thing you can apply for acidic and alkaline. You should get the right answer, okay? I don't think there should be a different answer coming up. You can try it out, but if you want to change it, you want to make your life easier, you can go for this one, 2 water plus 4, and this gives you oxygen there, then gives rise to 4 Y's minus, okay? Of course, E naught for that is different, but excuse me, whatever way you solve, you should be able to get the same answer. You will not get a different answers. You try and see what you get in both the cases. Good evening, Proful. How to calculate E naught at concentration? That I've already discussed to you. You use the Nernst equation, and then you will get it, okay? Substitute the Nernst equation. No, this is the question that is given to you people, right? You people, we have to solve it, okay? So these are the questions, if I am not mistaken. TS, I mean Sandeep and Abhijit. Are these questions you are given in the assignments or quizzes? Then I think you cannot give the answer here. I think you people have to work out. Please solve the things. Now what I am trying to look at is, let me just go here. How do you solve the problem? Let me go to that one actually, right? What's happening here? Why Why it doesn't go to next slide automatically? Huh? One more slide, no? Only that much comes, is it?
No, sir. This one.
Okay, yeah, that's the. Okay, you have to create that many slides or what?
Yes, sir.
It's laborious. Yeah. Okay, let me just see. Yeah, see, these are assignments. Now, you people cannot just ask the questions. You know, I think you guys are going to get marks, right? And not me. Okay. See, basically, you people should look at the governing equations, right? What are the governing equations? The governing equations are Nernst equation, right? 1, 2, the top kinetics, right? And third, of course, we talk about also, right? Okay. And the fourth, suppose you want to go a little bit more deeper into it, you can go to Butler equation, but I am not really going more details because it is not an electrochemistry course. I am not talking about it. So, you people have to be clear about these concepts, okay? I am not interested in what solution you are getting. I am interested in knowing whether you understood these concepts. If you don't understand these concepts, you cannot solve any corrosion problems. You cannot find any solutions at all, okay? So, you need to be just be thorough about it. Suppose, for example, do you have any doubt about this Nernst equation? Do you have any doubt about Tafel equation? Do you have any doubt about diffusion things? Do you have any doubt about Bartolomé equations in their application? That is the most important one. Otherwise, today I will say 0.01 molar, and next time I will say that no, it could be 2 molar. I mean, how do you find the answer for that? So you have to understand the concepts so that you can able to solve whatever problem that is given, which is of course related to the corrosion actually. So what also you need to know is, if people are not from the chemistry background, what you should know is, you should know the difference between moles, normality, that you should know about it, right? And you should also know about the equivalent weight, what it is. And I suppose this has all been studied, you know, in probably at the secondary school level or higher secondary school level. I do not see there should be a problem at all actually, right? So moles, normality, equivalent weight, you should know this concept actually. Atomic weight, how do you convert from atomic weight to equivalent weight? How do you convert from molecular weight equivalent weight? So these are the concepts you should be knowing, because when you talk about corrosion, I will say corrosion in 1 normal sulfuric acid. Corrosion may be in say 5 molar hydrochloric acid, okay. So how do we really do that? So then you have to know the basic concepts actually, what the clarity of this, okay. What is, for example, valency? Because see, iron, for example, corrodes as Fe2 plus. Iron can corrode as Fe3 plus. Well, totally different, okay. So this basic chemistry, they're not too much, but you should know actually. It is no other way that you can handle corrosion without knowing this basic concept. So for advice to all you people is to understand the basics of electrochemistry, and of course we have not gone much details of basics of electrochemistry, but I think to this extent you should understand, so that you can solve any corrosion problem without having any difficulties, okay. Yeah, how exchange current density determined in the laboratory is a good question, right? How is this done? I suppose you covered the experimental details, right? The experimental techniques you have covered. How do you carry out an electrochemical corrosion test, whatever, okay. Suppose we carry out a potentiodynamic polarization test, like you have a data which is log I upon potential here, and this is, let's say, towards positive side here, and this of course with respect to some reference electrode, whatever is a reference electrode you get here, right? And you will get something like this kind of polarization curves, right? And somewhere your E car is going to be lying somewhere here. Now what happens is, right, how do you get E car? You extrapolate this line, this is, isn't it? These are Tafel lines, right? These are Tafel lines. These are all the Tafel regions. You extrapolate this. The point that it joins there is ER, and the corresponding x-axis value is your log I car, right? What is exchange current density? You can use same Tafel line to get the exchange current density, right? What is the Tafel equation? Eta is equal to beta log I upon I naught, right? When eta equal to 0, what happens? When eta equal to 0, what happens? I becomes I naught, right? So draw the same Tafel line, draw a straight line here to a place where you have an equilibrium potential, right? This is your equilibrium potential, right? And this is going to be your exchange current I naught, because it says that when eta is 0, I is going to be equal to I naught. That's what it is, okay? So that's how. So extrapolate this line, this Tafel line, allow it to intersect corresponding to equilibrium potentials, and the corresponding current is called as exchange current density. This is for the cathodic reaction. Of course, you can also get for the anodic one by drawing a line here actually, okay. So it is possible to get it in the laboratory by using, of course you need to get a Tafel line, I mean clear Tafel regions. If the Tafel regions are not available, it is not possible for you to get this exchange current density at all actually. How to solve concentration problem? What do you mean by concentration problem? Can you please elaborate your question? Vijay? What do you mean by how to solve concentration problem? Can you be elaborate? You are not around, Vijay? Okay. Any other questions? Okay, so with that I thank you all. My coming back, my only advice I'll give is try to understand the basic fundamentals equations so that you can able to solve any problem. Don't think that I want to solve this problem. That is not the whole intention of learning actually. If you have any questions on, let's say, about Nernst equation, if you have any questions on the TOEFL equation, or similarly if you have any questions on the overall days relating to concentration and all these stuffs, for example, you should ask that. And once you are clear with these equations, then I think it is possible for you to solve any problems. So the assignments are given not to make you to solve that particular problem. The assignments are given very specially so that you understand the concepts. Okay, so that is the whole idea of giving assignments. Okay. Where concentration is given in the question, just like problem given in the assignments. Okay, you want some problem to be solved, for example, kind of things. What specifically is the question? Can you be very clear? Vijay, can you retype it? Can you rephrase your question? Can I be a little bit more pointed, Address your question to specific issue, of concepts. Okay, so you can also interact. I put the question above. Do you want to know what is meant by concentration? Yeah, Prof. Yes. Is there any effect of hydrogen pressure at 1 atmosphere, at 0.1 atmosphere on corrosion? Yeah, it is, of course. Will it be there or not? Can you use the Nernst equation? Do you think they will be changing or not? Will the Nernst equation same for both? Anyone can answer. All the guys who are attending, no? Can anybody answer this? Will the Nernst equation, if you put them in the Nernst equation, will you get the same value? What does the Tafel formula give you, right? Can you tell me what does it relates? It relates between eta, beta, I naught, right? Isn't it? Now in that equation, eta is equal to plus or minus beta log I by I naught. There is no concentration coming at all. Now, where does the concentration come in this actually? Can you just tell me? Will it come in the eta or not? Will that concentration take part in the eta or it won't take part in the eta? Yes, isn't it? It changes with ideal partial pressure, right? That's what I am saying. You please go. You expand eta, right? What is eta? Eta is equal to E equilibrium and also related to applied, right? So where does then the concentration come into picture? Where does it come? Does concentration come into picture in equilibrium or not? So you have to look at from that point of view. Please put all the things, on a paper, look at all the equations, expand eta. You expand eta, you'll know what happens. Yes, isn't it? It comes in Nernst equation, right? And the Nernst equation is, suppose I give an E applied is constant. If E equilibrium is changing, what will happen to eta value? That would change, right? So you write everything, everything. You take a piece of paper and start writing all of them on the paper. Because eta is related to E equilibrium and E applied, and E equilibrium is related to concentration. Is it or not? So you should now able to relate it. That's what I am trying to say. Look at that thing. Go back to the fundamentals now actually, okay? And you will get it. The whole idea of giving this problem is not to solve the problem. The idea of giving the problem is to understand the concepts, to understand the governing equations. That's why we are giving this. Yeah, right? Then you see, you can solve the problem. Okay, any other questions you people have? I know, see, one of the problem that happens here is that, in a classroom teaching is different from, what you read from video teaching. This is a problem. I do see this difficulty now, and it can happen to anyone. Okay, and but this also helps you people to do a self-study, self-learning. A struggle, but once you learn, and after that you will constantly able to solve the problem yourself without any teacher actually. Okay. Any other questions? Okay. So can I close it? Okay guys, thank you, and wish you happy reading, and let us start discussing through chat actually in normal times also, and try to get your questions clarified so that you are able to move forward. See, what happens is when you start, as a course develops with the time, it becomes a bit more complex. So only way that you can able to cope up with this clarity in understanding these ones. Yeah, but you can find out, equilibrium can be found out if all the values are given. You know the standard potential. Do you know or not? If you are given standard potential, you should be able to calculate. So I have given only today as an example for you, but I am not going to give like that every time, because I want you people to think. Because see, once you break the shackles, and it becomes easy for you. Because if you find answer now, for example, today, see, it doesn't take me just 1 second to give answer actually, frankly. But you would, in my view, will never catch that learning yourself. Okay, so try to break that log jam, right? And you should certainly will able to get it actually. Activity is not given. I don't know what is meant by activity not given. Can you elaborate what is meant by activity not given? Okay, so thank you very much, and see you guys next time. Okay. Thank you.
They can answer the question on forum also.
Yeah.